Mhm. So I think we'll get started. Couple of things I wanted to mention before we get into the notes is that we are going to collect your lab notebooks for the final project at the end of your last lab period. So that'll be Thursday, December 5th. And so if you're in the morning one, you'll hand in your labs not your notebooks by noon. For the afternoon group, you'll hand in your notebooks by just before 4. And so I put here a little list of things that we will be looking for in your notebooks. And so you can read through that on your own time. But the short version of it is clearly explain to us that you understand how all of the various subcircuits work and what they do. So what is the theory behind how they work? And then when you bring them all together and you hook them all together, how do they perform the analog to digital conversion? And so that's something that we will discuss probably in Monday's class. So in our next class on Wednesday, we'll talk about the circuits that you're gonna build on Thursday, which is gonna be the ramp generator and like a little gate circuit. So we'll talk about how all that works. And then the Monday, a week from today, we'll probably talk about how the overall analog to digital conversion works. So we'll do all that stuff in class, but it should be part of your notebook. The other thing I wanted to say is that I have put out an assignment 6, but we're not going to collect it and grade it. Nevertheless, you should try these problems because they're on some of the digital electronic stuff that we're doing. And by the end, I think, of today's class, you should more or less be able to do that whole assignment. And if you want to check your answers, because we're not going to collect them and grade them, I posted the solutions. Obviously, I strongly recommend that you try those problems first before jumping to the solutions. You all good? Here, shuffle them up. Okay, so good. So what I want to do today is I want to talk about the bipolar junction transistor. And so the way we're going to start this discussion is we're going to start essentially with a diode. So we're going to have a PN junction, and we're going to forward bias it. So we're going to make the P junction positive with respect to the N junction. And if we do that, what we would expect is there'll be a clockwise current, which corresponds to electrons going in the counterclockwise direction. If it's forward bias, then we overcome the potential barrier or the electric field that's established in this depletion region. And we can get the flow of charge across that junction. So the first thing we need to know about our transistor is that we are going to call these regions different things. So specifically, what we're going to do is we're going to end up with a base, collector, and emitter. This region here, the P region, will be the base region, and that's going to be lightly doped compared to the other regions. So what it means here is that we have in the N region these mobile electrons, and in the P region we would have mobile holes, but we're going to have much more mobile electrons in this N region. And so most of the current is going to be due to the flow of electrons across this junction. And so that's how I'm going to draw it. I'm going to draw most of these electrons crossing this junction. So start with black. When making, here, I'll keep this picture on there. When making a transistor, the N region is much more heavily doped than the P region. And so what that means is that most of the current is due to the flow of electrons. Now I've gone ahead and I've labeled the current IB and this resistor RB because this is going to be ultimately what we're going to call the base region. And so this is the resistor connected to the base region, and this is the current flowing into the base. Okay, all right, but this is essentially just a diode, right? Our diode was this one PN junction. If we forward biased it, we could get current to flow. If we didn't forward bias, if we reverse bias, we make this change the polarity of this battery, you would get no current to flow. So to make our transistor, what we're going to do is we're going to create a second PN junction. So we're going to put another N region on top of this P. So we'll have like the sandwich of N, P, N. Okay, so to complete the bipolar junction transistor, so BJT, a second PN junction is created on the opposite side of the P region. And what we're going to do is we're actually going to reverse bias the second junction. Okay, so this second junction is reverse biased. Whoops. All right, so let's see if we can draw that. We'll start by drawing the junction that we already had. There. So here's our original junction right here. This will be N, I'll call this junction 1. And then we'll have a second junction over here. This will be our P region. Here's junction 2, and this is also an N region. We'll have the same forward bias for this base and the first junction. So there's our base resistor, and we would in general have some current I base here. So now we have this other PN junction, and we're going to make that one reverse bias. And so that means we're going to make the N side positive with respect to this P side. And the way we'll do that is we'll use a second battery. We're going to connect it to the same ground terminal. So I'm going to call this ground. And we'll have our second battery right here. This will be positive, negative. And we're going to take that positive end and connect it over here through a resistor like so. Okay, so I'm going to start labeling these regions so we can start using the terminology that is common for these transistors. The central region is the base, as I've said already. And then the other two regions, this bottom one is called the emitter. And this top one is called the collector. So I'll label the batteries in a way that makes reference to the names of these regions. So this is the battery connected to the base and the emitter. So I'm going to call that V base emitter, VBE. And then we have this second battery connected to the emitter and the collector. So I'll call that VCE, the voltage of the collector and the emitter. And then this resistor is connected to our collector, so I'll call that RC. Okay, so that's good. Let's just label these depletion regions. So our first one is like so. So these are the fixed positive ions in the N-doped region of the emitter. These are the fixed negative ions in the P-doped base. And then that reverses polarity for the second junction. And we're going to have these mobile electrons that are going to cross the first junction because it's forward biased. But then the second junction is reverse biased. And so that means we're going to have an electric field that's pointing from the positive to the negative region. That's not compensated for by any battery, right? There still is a depletion electric field here, but we overcome that by using our battery to decrease that electric field. Here, we put in a battery that just enhances the electric field that's there. And so I'm going to call this the electric field across the base collector junction. All right. So that's the setup. And now we're ready to start discussing how this thing operates. let's imagine here that we have these electrons that are injected into the emitter. So we have this clockwise current, remember, so that's electrons flowing counterclockwise. So we inject these electrons to the emitter. This is forward bias, so they go across this junction. The electrons that drift over here and see this electric field, what's going to happen to them? Are they going to be repelled or pushed across? You have a negative charge encounters this electric field. Yeah, they're going to go across, right? The force on these electrons would be in the opposite direction of the electric field because they're negative charges. And so if they make it over to this second junction, they're just pulled right across. So that's the first thing to make note of. So electrons from the emitter are injected into the base. That's just because it's a forward bias junction. And then those that reach the depletion region of the base collector are swept across the junction by this electric field that we call the base collector electric field. When fabricating these transistors, what they do is they intentionally make the base region thin. And so that means most of the electrons that get into the base eventually do reach this region and are swept right across. The alternative is that they could flow out of this base terminal here, and some of them do that, but it's just a very few of them. Okay, so the base of the transistor is made thin. So let's say to increase the probability that the electrons reach the base collector junction, what we call junction 2. All right, so fair enough. So what I want to think about next is, well, what would happen if we kept everything the same, but then we just started turning up this collector emitter voltage? So we start making this a bigger and bigger voltage. That's going to add to this electric field, and it's going to get larger and larger and larger, and it's just going to expand this depletion region, the width of this depletion region. And as we do that, more and more of the electrons that are coming across the first junction are going to reach that expanding depletion region, and more of them are going to go straight into this collector region. Okay, so increasing this voltage across the collector and emitter, BCE, extends the depletion region at the base collector junction, which allows more electrons to be swept into the collector. And what that will do is, if we look at this picture again, I'm going to label the current going into this terminal as IC. Okay, and so let's put that in there. And yeah, So I'm going to label this current IC. And so as we have more and more electrons flowing right through this transistor to the collector, they come out here and we're going to have this corresponding current in the opposite direction. So as we increase this voltage, we enhance that collector current into the collector, which increases IC. Okay, so what I want to do is I want to start plotting this IV characteristic like we did for the diode. So what we're going to plot is the collector current on the vertical axis and the collector emitter voltage on the lower axis, on the horizontal axis. So V collector emitter. And so what we just said is, as we increase this voltage, we expect the collector current to increase. And so I'll indicate that something like this. Okay, we're going to add to this plot. So let's continue below. Well, we could keep doing that. We could keep increasing this collector emitter voltage, but at some point, essentially all of the electrons that are injected into this emitter are going to go across the transistor into the collector. And once we have 100% of electrons reaching this junction, then, turning up this voltage more doesn't do anything because all of the charges are already crossing into the collector region. And so we reach this plateau where the collector current no longer increases. Okay, so at some point, essentially all electrons reach the collector and increasing the collector emitter voltage no longer changes the collector current in a substantial way. Okay, and so what that would look like is we keep increasing this collector emitter voltage and the collector current increases, but then at some point, basically all of the electrons have reached the collector, and so there's no more to kind of capture, and we get this plateau of the collector current. All right, there's one more thing we could do. We have two voltages to tune, and this one is the collector emitter voltage. If we go back and look at our diagram, we also have a base emitter voltage. And so let's think about this. Let's imagine that what we've done is we've turned this collector emitter voltage up so high that we've plateaued our collector current. There's no more electrons to sweep across, but we could increase this voltage, which would increase the rate that we inject electrons into the emitter, and that should enhance the current as well. And it would enhance the current no matter what this collector emitter voltage was, because we'd always be injecting electrons at a higher rate as we bump up this voltage and the corresponding base current. Okay, so increasing the base current, which is dq by dt, which we can do by increasing what we call the base emitter voltage, increases the rate that electrons are injected into the emitter and therefore increases IC for all values of the collector emitter voltage. All right. So let's imagine we did that. So we had this one curve which corresponds to some particular value of the base current. And then we increase the base current again, just a little bit, and we should get a corresponding curve that looks something like this. It's the same sort of thing, but we always have a little more current because we're supplying the emitter with more electrons. Of course, we could do the opposite. I could turn down the base current and we would get a curve that looks something like this. And we could keep doing, and we get this family of curves that looks something like, whoops, family of curves that looks something like this. And this is a very characteristic kind of IV plot for a transistor. So what we should do is label some of these. This is a low base current or base emitter voltage, and this is a high base current or base emitter voltage. All right. So that's sort of the starting point for understanding this transistor. What we're going to try to do is we're going to try to operate this thing as a switch. And rather than keep drawing all these base emitter collector junctions with fixed charges and mobile charges, we're going to adopt a circuit symbol for our transistor. So the transistor circuit symbol. And so for us, we're working with the bipolar junction transistor, and we're going to work with one that is the NPN configuration. So the sandwich with the P in the middle. And the circuit symbol looks like this. This is a 3-terminal device. There's the base, and then there's a collector, and there's emitter. And the way they distinguish the collector from the emitter is there's a little arrow on the emitter terminal. And so this is NPN. All right, so if we were to draw a simplified version of the circuit that we just discussed, what we had is a base emitter voltage connected to a resistor RB. And that was going into the base of our transistor. And then we had our emitter connected to ground, like so. And then we had our collector, and there was a R collector. And then we had a collector emitter voltage. So that's the circuit we had. If I was to draw the currents, we would have I collector, I base. We labeled those ones on our previous diagram. I'm going to now label the third one, and this would be the emitter current. Just looking ahead, what we're going to end up doing is we're going to do like a Kirchhoff junction rule, which says all the current into a junction has to be equal to the current flowing out. And so what we have is current I base and I collector flowing into our transistor and I emitter flowing out. And so we will adopt this junction rule that I base plus I collector is equal to I emitter. And that will be part of our analysis. So this is the circuit we've been analyzing above, just drawn with the transistor circuit symbol. All right, so because the base is thin, most electrons from the emitter cross into the collector. All right. So if that's true, most of the electrons flow right through this transistor in the configuration that we've drawn it. And so that means there's not many of them that are leaving through the base. What that implies is that these two currents are approximately equal to each other, and the base current is very small. And so therefore, I base is always small. You know, it might be typically in, say, the microamp range, whereas the collector emitter currents could be sort of tens of milliamps, something like that. Okay, so by the junction rule, which we just referred to, we would expect that I base plus I collector, which is the current into our transistor, has to be equal to I emitter. But if I base is small, if this is really small, I mean, it must be true that the collector and emitter currents are about equal. But since I base is small, I collector is approximately equal to I emitter. And what people typically do when talking about these transistors is they introduce this parameter alpha. And they say I collector is equal to alpha times I emitter, where alpha is very close to 1, right? It's slightly less than 1 because the collector plus base equals emitter. So this emitter is always the bigger current. And so alpha is something a little bit less than 1, and that will tell us our collector current. So this is where alpha is approximately 0.99999 typically. And so the precise value will be determined on the fabrication of the transistor. What are the doping levels in the 3 regions? How thin is the base compared to the others? Things like that. Okay, so if that's true, we would say, let's say I base, if I solve for I base, it's going to be I emitter minus I collector. Okay, so it's I emitter minus I collector, which is I emitter 1. So if I write this as alpha I emitter, I can factor out the I emitter and I get I emitter 1 minus alpha. And so what I'm going to do is I'm going to take the ratio. Oh, whoops, that's not what I want. I'm going to take the ratio of the collector current to the base current. The collector current we said is alpha I emitter. And the base current we just worked out is 1 minus alpha times I emitter. And so this is alpha 1 minus alpha. And this is usually defined as beta. So beta. And if you look up like a data sheet for a transistor, they will likely quote this value of beta for you. If alpha is 0.99, this is 0.99 divided by 1 minus 0.99. So it's 0.99 divided by 0.01, which is 0.99 times 100, which is 99. So beta is usually around 100, maybe a little less than 100. And so one thing this tells us is that the transistor is like a current amplifier. It can be used as a current amplifier. So if I supply some small base current, the resulting collector current is about 100 times bigger than that. So we get a large current gain. And so I collector is equal to beta times I base. And so in this way, our transistor can be used as a current amplifier. Okay, good. So we're basically at the point where we can start to use the transistor in the way that we want to use it. The application that we're interested in, and in fact, the one that we will use in the final project, is using the transistor as a switch. Transistor as a switch. Okay, so in fact, the circuit we're going to analyze is just like the one that we've been discussing. We're just going to add an output terminal. So we're going to specifically, we're going to say, let's take our input voltage as the voltage that we supply to the base. And so we're going to have our base resistor. And then here's our transistor. We will take our collector over here. Here's RC. And I'm going to call this VCC. We will connect our emitter to ground, like so. And so this is collector, base, emitter, and it's also NPN, like so. And what we're going to do, the only thing we're going to add is we're going to take our output right here. So we have now an input and an output. So I'll label the currents like we did before. This will be I base, this will be I emitter, and this will be I collector. Now, one thing we can do right away is we can say, if I start here and work my way to the output, I would say VCC minus ICRC is equal to V out. Okay, so we have V out is VCC minus ICRC. And so what I want to do is I want to consider two cases. So, and I want to keep this on here. So case one. Let's start with V in less than 0.7 volts. The entire previous discussion assumed that the base emitter junction was forward biased. And in that case, we would want this V in to be above 0.7 volts. And so right now I'm considering the opposite case where it's less than that. In that case, this first junction, the base emitter junction, is reverse biased. And we're not going to get any of the electrons crossing that junction and drifting over to the base collector region. And so everything we said is not going to happen. We're just not going to have any current flow. So in this first case, the base emitter junction is reverse biased. And that implies that the collector current is going to be 0. We could go back to our picture here. And so we said low base currents would correspond to this, like a small collector current. If I say the base current is going to be 0, then we're going to get 0 collector current. Okay. All right. Okay, but if the collector current is 0, and we said the V out is VCC minus ICRC, this is 0, and so V out is just VCC. Okay, so therefore V out is just equal to whatever that voltage is near the collector. All right, so that's case 1. So let's do the opposite case, case 2. Let me emphasize something here. What we have is a small input, and now we're getting a large output. Okay, so that's one thing to keep in mind. So case 2. Let's say V in is much bigger than 0.7 volts. In that case, our base current is relatively large. Like the base current is always small, but I can make it relatively large by increasing that base voltage. So instead of 0, it might be like 10 microamps or something like that. And if the base current is large, then the collector current is large. Again, we could see that in this plot that we made. As we increase the base current, the collector current keeps getting higher and higher and higher. All right. So therefore, the base emitter junction is forward biased. And that means that the collector current is not 0. And so therefore, V out is equal to VCC minus IC over RC is going to be small, right? In the first case, this was 0, so that thing just vanished. Now this is some non-zero contribution, and so we're subtracting off of whatever that VCC is, and we end up getting a smaller output. So as we increase this current, as we increase the collector current, the voltage at this node keeps getting smaller and smaller. This is the voltage at the collector. Now, the base we made as a high voltage, and now the collector is becoming some low voltage, and eventually what will happen is we're going to make both of our junctions become forward biased. So eventually, for sufficient IC, both the base emitter and base collector junctions become forward biased. And in some sense, that's like having 2 forward bias junctions back to back. It's like having 2 forward bias diodes back to back. And we know that when we have a forward bias diode, we have a voltage drop of 0.7 volts across it. But because the junctions have opposite polarity, we first drop 0.7 volts and then we gain 0.7 volts or vice versa. And the net is almost 0 voltage across the entire transistor. And the result is that V out is close to 0. Okay, so let's construct a truth table for what we've just talked about. So V base and V out. So we said if we made V out low, which was the first case, less than 0.7 volts, we said the output was going to be VCC. We could set VCC to be something like 5 volts, and that would correspond to what we were calling high in our digital logic circuits. And then in case 2, we said, well, let's make V base some large voltage. Maybe we'll make it VCC. Okay, so then we have a high voltage at the input, and we said our output is going to be close to 0, which is a low. I could redraw this truth table kind of in a more abstract way, where we could say the input, this is V in, right? V base is equal to V in. 0, 1, 1, 0. And what does that truth table look like? It's an inverter. So not only have we used the transistor as a switch, so when I have a low input, my output is some VCC, and I have no current. When my input is high, I have 0 output, and I have a lot of current through my transistor. So we're using the transistor to turn current off and on. And at the same time, it's functioning as an inverter. So this circuit that we drew is acting as a current switch, switching IC off and on, and acting as an inverter at this output. So in fact, what we should do, what I want to do is I want to add a column to this first truth table. We'll say V in, which is equal to V base, and I'm going to put IC here. So if we said this was 0 or a low, then our current was equal to 0. And if this was VCC or high, then our current is not equal to 0. So we can turn the current through the transistor off and on using V in. And so this is the switch capability, and the truth table is that of an inverter or a NOT gate. Okay, so let's just summarize what we said. Here's VCC, here's our collector resistor, here's V out, then this goes to our transistor. There's our base resistor, this is V in. And so that is equivalent to our NOT gate, V in and V out. And we can control at the same time whether the current through the transistor is off or on. Okay, good. How much time do we have? We have 6 minutes. Let's do one other thing. We've only made one of our logic gates. We've made the NOT gate. Notice that it's a 2-terminal device. It has a 3rd terminal, but that's like the power terminal. So remember, the inverter chip to be used properly needs to be powered, and it needs to have a ground connection. In the chips that we use, the power was going to, like, I don't know, pin 14 or something, and the ground was pin 7. So those are those connections, and then we have an input and output left over, and so that corresponds to this. All right. So what about other logic gates? Well, let's consider the following. Let's consider a series combination of 2 transistors. All right, so what we'll do is we'll have the same sort of circuit that we had before. We're gonna have VCC up here, and then we'll have our collector resistor. Sorry, I've already drawn my collector resistor, RC. So then we'll have our transistor, and then we'll have our base and an input, right? So this is, if I put my ground here, this is the exact circuit that we just analyzed, that's the inverter. But what we're gonna do now is we're gonna put in a second transistor, and we'll put it just exactly in series like this. And we'll add, we have another base, so we'll have another base resistor, and I'm gonna call these inputs A and B, and I'm gonna take my output like we did before over here. So here's V out, and V out is still VCC minus ICRC. Okay. Transistors in circuit diagrams are usually labeled as Q for some reason. So I'm going to call this transistor A, QA, and this is transistor B, QB. And we're going to try to construct a truth table for this thing. All right. So what we have are two inputs. And the possible combinations of inputs are like this. Right? It could be high or low, let's say. And what I'm going to try to do is I'm going to try to indicate whether a transistor is allowing current to pass or not. And then we'll label what the corresponding current IC is. So we'll label IC up here, IC. And then finally, we'll put what V out is. All right. Just forget about the second transistor. What do I have to make A in order to have non-zero current through the transistor? Is it high or low? I need to forward bias the base emitter junction. So is A going to be a large voltage or a small voltage? A large voltage, okay? So whenever A is high, then we have current flowing, the potential for current to flow through this first transistor QA. And so what we'll say is that when A is high, QA is on, or it's conducting. If I make this 0, then this first base emitter junction is reverse biased, no current. And so we'll call that QA is in the off state. All right. Same thing for QB. Whenever B is high, that second transistor will be conducting. So on and on. And whenever B is low, the second transistor is not conducting. So we have off, off. Now, the only way I could have current flowing from VCC to ground is both transistors have to allow the current to pass through. And the only time both transistors are conducting is down here when A and B are both high. So the only time the current is not equal to 0 is when both transistors are conducting. Here, both transistors are off, neither of them would allow current to go through. In either of these cases, one of the transistors is on, it would allow current, but there can't be any because if one's on and the other's off, I can't run current to ground. And so in all these other cases, the current is 0, and the output is VCC minus IC times RC. If the current is 0, the output is just VCC, say 5 volts. And so we're going to get pi for all those. When the current is not 0, we get VCC minus some large number, and so this is close to 0, and we get a low output. So if I want to summarize that truth table, what it ends up being, if we look at just the inputs and outputs, it's 1, 1, 1, 0. What's that truth table? That's the NAND gate, yeah, it's the NAND gate. So this is the transistor implementation of a NAND gate. Okay, good. So that's where we'll stop. Next time, we'll review what we said about the transistor. We will write down the transistor circuits for the NOT gate and the NAND gate again, and then we'll work on some of the others, and we'll preview what we're going to do in the lab on Thursday. All right, great. Thank you very much.